So the last topic we're talking about today is the Poisson distribution, which is section 6.3. Again, here's the learning objectives we'd like to get through. Just like we had criteria for a binomial distribution, we have criteria for a Poisson process. The probability of 2 or more successes in any small subinterval is 0. The probability of success is the same for any 2 intervals of equal length, and the number of successes in any interval is independent of the number of successes in a different interval, provided those intervals are not overlapping. So this is a little bit more complex understanding than what we saw with binomial distribution. A good example we used was the FDA. Gives a level of how much foreign substances can be in our food. So the level for insect filth in chocolate is 0.6 insect fragments per 1 gram. So the probability that there's no insect fragments is going to be 0 at some point in any small subintervals. But the probability that there is insect fragments is going to be the same in intervals of different lengths. It could be 0.6 in this 1 gram of chocolate. It could be 0.6 in this next gram of chocolate. But they're not dependent on each other either. They're those grams of chocolates don't overlap. We measure gram by gram, and the amount of bugs in this one does not determine the amount of bugs in the next one. Sorry for the kind of gross example. Just like we had a distribution function for the binomial distribution, we have a function for the Poisson distribution. It's a little bit more complex. X is still the number of successes. Our interval has a fixed length of t, but we get this lambda thrown in, okay, that kind of upside down y. And it represents the average number of occurrences in an interval that is length 1 to length e. And if you don't know e, it's 2.7, 1828, 1828. So somewhere between that interval, that's an average of occurrences, lambda. Okay? So given what we know about the FDA and insect parts in our chocolate, we can compute the probability for the number of insect fragments in a 10-gram sample of chocolate. We want to know if it's exactly 3, fewer than 3, or at least 3, so 3 or more. Okay? So let's go ahead and look at how we could do that. So lambda was 0.6, the average we got that from the problem. We also got 10 trials, or an interval of 10, from the problem, 10-gram sample. So we can plug that into our formula. So lambda times the length of the interval cubed. Because we wanted the exactly 3 trials, or 3 successes, over 3 factorial times e to negative lambda times the interval, and that gives us this 0.0892 number. Then we wanted less than 3 occurrences, so that's less than or equal to 2. Those are the same idea. So we could have 0, we could have 1, or we could have 2, but we can't have 3 because it's less than 3. So again, we're going to fill this out for 0, and then for 1, and then for 2, and add all those up, and we get this. With greater than 3, we're looking at 4 occurrences, 5 occurrences, 6, 7, 8, 9, 10. And that's a lot to add together. So it'd be easier if we just did 1 minus px less than or equal to 2, which we had above. So This idea kind of looks the same from that example we had in the binomial distribution, in that we can rewrite these things, the probability less than or greater than, to help us solve what we want instead of doing a ton of work. Okay? The mean of a Poisson distribution is lambda times the interval. Just like in a binomial distribution, we had the number of trials times the probability of success. Here we have that lambda times the interval. The standard deviation is a lot easier than what it was in binomial. It is just the square root of lambda t, or the square root of the mean. So if we look at the distribution function differently in terms of the mean, what we're really getting is mu raised to the x, because remember in our formula here it was lambda t, which is the same as mu. So we can fill that in, over x factorial e to the negative mu. So we can take that same example and work through it a little bit more. And we want to find the mean number of insect fragments in a 5-gram sample of chocolate. Well, we said lambda was 0.6. This time our interval is 5. We multiplied those together. We have 3. So we would expect 3 insect fragments in a 5-gram sample of chocolate. That's how we interpret that. That would be the mean number. Could we have more than the mean? Maybe. Probably not healthy. Could we have less than the mean? Sure. The standard deviation, we're just going to take the square root of 3. And that finishes up the Poisson distribution.